All right, we're going to talk about parametric equations, what they are, what they're used for. Parametric equations is a huge field, if you will. There's a bunch of stuff you can do with it. We're going to be narrowed and focused. So what if we want to go backwards? What if we already have a Cartesian equation, we want to get it into parametric form? Well, we need two equations, and the easiest way to do that is just say, okay, x is t.
Yeah, see, so this comes like cheating. But basically, we're just going to say we need a parameter for it, so we're just going to replace x with t. Now, there are issues there where if we wanted to get more in-depth into this, where we wouldn't want to do it that way.
Right.
But for us, for now, for our purpose, it's good
Let's
enough.
try it that way. So the second equation would have to be a horizontal, or a vertical component, rather.
So we have
we're
one
going to
right
replace our x's with t, because they both have to have the same parameter.
And we're done.
We're done. We need both equations, because it's a pair of parametric equations.
That was exciting.
Alrighty.
I hope the test is full of those.
Next.
Okay, so what was the point of that question? It seemed really simple.
It did.
Earlier in the year, we did, what did we call it?
Projectile
motion. I knew it
Yes.
started with a P, and it wasn't parametric that time. Projectile motion. We threw things across the room. We threw things up in the air. The problem is that we modeled. I'm having a hard time talking today.
That's all right. I got you.
We modeled the height of the function in terms of time with negative 16t squared plus initial velocity times time plus initial height.
Yes.
But when we graphed that, we graphed time versus height, and it always gave us a parabola, and we started here at h naught, and we basically had an upside-down parabola.
Right, of course, because it was t squared, which is quadratic.
And the point we're trying to make here is that this picture didn't look any different, though, if somebody threw the ball straight up or if somebody threw a ball across the room.
Yeah, no, it didn't.
And to kind of illustrate that, I want to show you this. So what I want to show you here is a graph of a ball going up in the air and a ball going across the room. And I want you to see that basically the one on the right is a ball going up and the one on the left is the ball going across the room. I want you to notice that their heights are the same.
I'm pretty sure I threw the ball on the right, and it only went straight up.
If you threw the ball on the right, it probably would have gone straight down.
Hey! You're so mean to me.
Okay, so generally speaking, we can see that both balls have the same height here as they're going back and forth, right?
Right.
And I want to show you why. When I go to the equations here, we'll talk about x was t, that's what we did earlier.
Right.
And we made y negative 16, blah, 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 but we had t squared plus 76t plus something else. The same equation is in y2 down here.
Correct.
Right? y2 is the same equation as y1t, but now x2t is 6.5, which means that I made the x value stay at 6.5, not move at all.
Okay.
That's why the ball went up. But the heights were the same exact height.
Yes.
All right, this is not useful for us most of the time if we really want to model the path of a ball going across the room.
Right, because I want to know how far I hit the ball.
Right, so what parametric does is it gives us a chance to graph the position of the ball, and if it went like this, we will know the horizontal and vertical position of the ball, and we'll know the time at which it arrived there.
Okay, so more information.
Than we may need, but let's try it out. So we need to redefine this definition. In the last example, we let x equal t,
Right.
and then we let y equal negative 16t squared plus v naught t plus h naught.
Because we said that was the simplest way to do it. But let's go back a second to what we did the last class, which was vectors.
Vectors, component form of vectors specifically.
Okay.
And a velocity has a vector. It has a horizontal and a vertical component to it.
Yes, it does.
And since the velocity itself is really the magnitude of that vector, and
Okay.
the angle at which we launch it can be written as theta,
Yes.
then the component form is going to be v naught cosine of theta, comma, v naught sine of theta.
Okay.
That's supposed to be.
And it's a vector. So you're telling me that we need to talk about our x direction and our x position in terms of this velocity.
Right, so what we're going to do is we're going to stick this basically in front of this t, and we're going to stick the velocity of the vertical component of the velocity
In place of
in
the
place
velocity.
of v naught.
Okay.
But the horizontal component is also going to have a velocity component to it.
Okay, so we need some new equations here.
We definitely need some new equations.
Okay, so they've been sitting and watching. Pick up your pencil.
Yeah, pick
Write
it up.
this down.
All right, so
All right.
x is going to be v naught
Yep.
cosine of theta
Yep.
times t.
T, the parameter. Okay?
In the the vertical component of
Let me
this.
see if I got this. It's going to be negative 16t squared, because that's not going to change. Plus, but instead of our v naught t, we're going to have v naught sine theta t.
And then times t. Now keep in mind, the angle is what you're taking the sine and the cosine of, not the angle times t. So
Correct.
it's sine of the angle, close the parentheses, then times t.
Okay, and then plus our original height, or our h sub 0, h naught.
So now when we graph this, we're going to be graphing not time versus height, but x versus y.
Right.
And it'll go across the room like this at some angle, hopefully.
Correct.
And we get more of an actual motion, which we have an x and a y, and we'll know what t value it
Got us
occurred
there. Okay. Well, let's see how this problem's going to look. Let's try example 4.
at. Let me just throw the
Do you
markers
need
down.
me to write for a second?
Maybe.
I'll be clue.
Go figure. All right, so specific example. A baseball is hit 129 feet per second at an angle of 30 degrees relative to the level ground, as opposed to the flat ground or just the ground.
Unless
From-
it's on a hill.
Why would you play baseball on a hill?
I don't know.
All right, an initial height of
Maybe
3
that's
feet.
why mine hits the ground.
Write the two parametric equations. All we're going to do is plug in 129 for V naught, 30 degrees for theta, and 3 for H naught, and we're going to repeat the equations that you have written right above here. So while Mrs. Goldfield writes all that wonderful stuff down, you should too.
I lost my
30.
angle.
Times t, and then y is
that.
equal to, yeah, those parentheses will help you because otherwise you get in this bad habit of multiplying the 30 times t for the cosine and you get wrong answers. Now we could take this a step further since we know sine of 30 is a half, but we're just going to use our calculator for this entire process, so don't worry about it.
And not every problem that you're going to get on the worksheet is going to be a nice angle of 30 degrees,
No.
so we'll see how that looks. All right, so let's make sure we have an understanding of this. After 5 seconds, I should be able to figure out how far the ball's traveled horizontally and how far it's traveled vertically, because this 0.5 seconds is simply time.
Okay, so that's our t.
That's our parameter.
So if I want the horizontal traveled distance, I just plug in 0.5 to my t. That part of the board just doesn't work real well, does
That's
it?
so well.
The top and the bottom working better.
That's a 5.
It just looks like terrible.
Shush. It's a 5.
All right.
What's my answer?
Your answer is 55.859 feet.
Okay.
3 decimal places. All right, the vertical component is y equals negative 16 times
Oh, sorry.
0.5 squared.
I knew that.
We actually have a number for t now. We don't have to use t. Negative 16, parentheses, 0.5 quantity squared, plus 129 times the sine of 30 degrees
You know, you're being sarcastic.
times 0.5 plus 3 is approximately or equal to 63.5. It actually comes out to be nice and neat because the sine of 30 was 0.5. Does that little mark mean feet?
It does mean feet.
It's like
I didn't-
63.5 prime.
Feet.
It's my world. Okay. Determine whether the ball will clear a 10-foot wall 400 feet away. All right.
So
Well,
wait.
first things first. We could do this algebraically. What would we have to figure out if we were going to do this algebraically?
Okay, so if I want to know if the ball is going to clear the wall and the wall's 10 feet high, then I need to know, 400 feet away is a horizontal distance.
Yes.
So I would put a 400 right here and determine what time creates a 400 distance.
Good. So if we
Okay.
know the time, basically we're going to say it had to travel 400 feet, and we want to know how long it took to travel 400 feet.
Correct, and then I would plug that in to see what the height was, and so I'd have to put it there and
So how would we
there.
know if it clears the wall if we did that?
Well, if the height is more than 10 and the wall is 10 feet tall, then I went over the wall. Yay
Right.
me.
And if the height turned out to be negative 8,
Then I didn't even make it the
yeah,
400
right,
feet.
it bounced way before it reached the 10-foot wall. Would you agree?
Okay, that seems like a lot.
It is a lot of work, and we have a calculator here, so it's more fun to do this with a calculator. So, and I'm going to go ahead and go to y equals, and I want to show you a couple things here. I have a x2 graph that is 129 cosine of 30 times t, which is my horizontal component.
Okay.
And my y2 graph is negative 16t squared plus 129 sine of t and blah, blah, blah.
Sine 30 times t. Yeah.
I have x1 is 400 because I want the wall to be 400 feet away.
Okay, and that's a
So I'm
horizontal
going to
distance.
keep x at 400 all the time. It's not going to change.
Okay.
The y is 2t, and really what that is it's 10 divided by 5 times t. The 10 was for the height of the wall. We have our window set for 5 seconds. So
Okay.
when time reaches 5, which 10, those 5s will cancel, and my wall will be 10
10
feet
feet
tall.
tall. Okay.
You don't have to know how to do this, by the way. It just makes the pretty picture on the calculator. I
kinda
just
fun,
wanted
though.
to explain it.
Some
So
of you
again,
will want to know.
the first equation is for the wall,
Okay.
and the second equation is for my the path of the ball.
Okay.
I have it set up. I took the simultaneous part off, so it would graph the. I took the simultaneous part off, so it would do sequential, so it'll graph the wall first. So here we go.
Okay.
We graph the wall, and then the ball gets shot through the air and clears the fence.
Yay!
Home run.
I'm pretty sure I hit that.
Lots of fireworks,
Yeah.
as long as there's not a fire ban. Okay, I got the I went ahead and moved the trace button so I
Okay.
could see that time 3.6,
Gives us a horizontal distance of 402, so that's
which
past,
is past
the wall, and a vertical distance of 27.84. So 27.84 is clearly still pretty high above 10 feet.
Yeah, that's a big home run.
Yeah.
Mike Trout. Go Angels.
All right, we'll do a few more of these applications in class, and we'll see you then.